When an agent enters reasoning mode, the workflow stops. Before it can take its first action, it must generate a hidden chain of reasoning tokens, a process that repeats, in full, for every single request. This chart tracks generation cost. On GPT 5.4 Mini, enabling reasoning mode triggers a massive token spike, requiring 3 to 5 times the baseline compute per episode. Larger models scale this further. Qwen 3.627b hits 6.2 times the standard token count. These reasoning tokens are hidden from the user, but they are generated afresh for every request. Unlike a one-time training phase, this expense is recurring. You pay for it every time the agent is invoked. The result is a direct hit to both latency and compute costs on every API call the agent makes. If you scale an agentic workflow under this paradigm, your lifetime compute costs will grow without bound as your volume increases. To find a more efficient path, we have to run a forensic analysis on what the model is actually doing during these expensive reasoning phases. Most domains are governed by episode invariant procedures, rules and protocols that never change between different tasks or different users. In retail workflows, the agent must always authenticate a user before fetching their order history. That rule is constant for every single caller. Logs reveal a paradox. The model spends its reasoning budget re-deriving invariant rules rather than solving instance-specific logic. It builds a complex logic tree to open an authentication gate, resets, and builds the exact same tree on the next request. We see this again in the AlfWorld benchmark. The model consumes thousands of tokens to deduce that heating an object is a single atomic command, rather than a complex series of door-opening maneuvers. Paying a 6-time premium to continually rederive static facts is a structural inefficiency. In traditional software, we would solve this by amortizing the cost offline. This paper introduces passive skill distillation, an architectural shift that amortizes this recurring compute tax. Stage 1 of the offline pipeline is simple. We collect a trajectory corpus of 35 to 50 logs from the existing training split. These logs contain the raw history of the agent's work, the environment observations, the actions taken, the tool calls, and the final rewards. Because most production systems already log this data, the process requires 0 new active rollouts. These logs don't even need to contain reasoning traces. Standard, non-reasoning trajectories provide enough information to identify where the agent succeeds and where it fails. By utilizing existing logs instead of active data collection, the initial acquisition cost for this method effectively drops to 0. In Stage 2, we deploy a dedicated coding agent, like Claude Sonnet 5, to analyze those logs. The agent is strictly sandboxed. It receives a fixed natural language instruction and is completely isolated from the live environment. It can only read the files you provide. The agent writes its own Python scripts to scan the corpus, filtering for failure frequencies and common action loops across all 50 trajectories. The result is a distilled skill file, 40 to 130 lines of markdown text. These rules are imperative and statistically traceable. They identify specific bugs that appeared in the majority of failed rollouts, providing a clear instruction for the model to follow. Compiling this entire skill for a domain costs between $1.28 and $2.44. This one-time investment in compilation shifts the economics of the agent. It converts the reasoning premium into a fixed prompt prefix, replacing a logic tree the model must rebuild with a set of instructions it simply reads once. In Stage 3, the compiled skill is injected directly into the non-reasoning model's system prompt. The infrastructure remains unchanged. The available tools, the decoding parameters, and the agent harness are exactly the same as the baseline. This method relies on provider-side prefix caching. By caching the system prompt, the marginal input cost of adding the 130-line skill becomes negligible. The results on GPT 5.4 Mini show that this injection recovers most, and sometimes all, of the reasoning accuracy gap. In benchmarks like AlfWorld and Retail, the non-reasoning model with the skill actually outscores the reasoning model. This accuracy is achieved while using nearly 6 times fewer tokens per episode, significantly reducing the total cost of each run. The AlfWorld results highlight a surprising efficiency gap. In tasks like cooling a tomato, the non-reasoning model with the skill beats the reasoning model. The reasoning model often gets trapped in appliance store loops, burning its token budget on redundant checks. The distilled skill acts as a hard guardrail, forbidding these loops and defining adjectives like cool as specific atomic actions. An invariant rule, aggregated and perfected from 50 past episodes, proves more robust than a live derivation that an LLM must execute flawlessly every single time. To understand these results, we can look at two different ways the model searches for procedural knowledge: deep versus wide. Deep search is test-time reasoning. It builds a vertical logic tree inside a single episode, rediscovering rules from scratch, paying the token cost every time. Wide search is passive distillation. It scans multiple trajectories simultaneously, identifies regularities, and extracts a single shared rule. Both methods aim to provide the same result: procedural knowledge. They just use different cost structures to get there. When the knowledge required is identical across every episode, width offers a better return than depth. In these domains, the distilled skill matches or exceeds reasoning accuracy while bypassing the recurring token premium. But distillation is not a universal replacement for reasoning. In this gap analysis chart, we can see where wide search reaches its limit. On telecom and spreadsheet tasks, the reasoning model still maintains a clear accuracy edge over the distilled skill. These domains are defined by instance-specific knowledge, volatile factors like unique spreadsheet formulas or specific telecom dependency chains that change with every request. A static prompt prefix cannot adapt to these one-off anomalies. These tasks require the live, instance-specific deliberation that only a reasoning mode can provide. Deployment also carries its own constraints. These skills are highly specific to the model they were distilled for, and we don't yet know how much the results vary between different distillation passes. Ultimately, deep and wide search function as complements. High-volume, invariant procedures are best handled by distillation, while expensive reasoning is reserved for the instances that truly demand it.